3. We are talking about similar figures. And what similar figures is, it is the same figure, or I'm going to say shape, the same shape. The only difference is they are of different sizes. So the same shape, different size. That is the definition of similar figures. So if I say that two shapes are similar, that means that they are the same, they just are different size. For example, look at the circle. They are similar. One is smaller than the other, but they're identical. Or if I look at the square, I got a small square and a big square. It's pretty much just like enlarging the shape. Or if I look at it, this triangle and this triangle. Now what the book and what the worksheets and stuff, what they try to trick with you is they might take a shape like this and they're going to say, are they similar?
Yes.
Yeah.
They are. One's just flipped. So you gotta be able to actually visualize rotating it. And I can't do it. You gotta be able to rotate the shape and say, okay, yeah, I can make it get in the same form. What corresponding means, corresponding is the related side lengths. When I say related side lengths, I want you should have had these two triangles drawn in your notes, and I want you to just label the vertexes. Vertex is points. So I'm just going ABC, that's triangle ABC. This is triangle DEF. And when I say corresponding, that means related. So it means it's like it's a little matching. It's like if you were to compare the side length. That's what it would be. So how we say that, we would say AB corresponds to what? If I was like AB, if I'm looking at that side length, what side length does it correspond to on the bigger triangle? DE. So I say AB corresponds to segment DE. Now notice how I'm writing this. I'm writing this with a bar on top. That means it's a segment. So I'm saying segment AB corresponds to segment DE. Okay? Now, if I start at this point, this A, then I need to start at its corresponding vertex. I need to start at this, DE. I cannot say, this is no, I can't say AB corresponds to ED. You can't work backwards. I know some of us, it's pretty natural for us to just do the same, but some students will write ED, and then I'd have to count it wrong because it's not corresponding. Okay. All right. And then if I looked at segment BC, what does BC correspond to, class?
Yeah.
Yeah, right? BC corresponds to, where's its match? Here it is, there it is, there's its match. EF. So segment BC corresponds to segment EF. Right, now on my last one. And I'm going to say segment CA corresponds to what? So I'm going, huh?
FD.
Good job, because I was trying to trick you guys. So I'm saying segment CA, so I go from that vertex all the way back to the original. CA corresponds to, I better say FD. I erase some of that D. This is a D. So part of your homework expectation today is to be able, if you know that two triangles are similar, you can identify corresponding sides. And that's what I did here. This is identifying corresponding sides. That's what we just worked on. All right, next.
All right.
The properties of corresponding triangles. Their corresponding angles have the same measure. We're not going to work too much on that, but this is the biggie. Corresponding sides are proportional. So when I say they are proportional, that means that I am going to be able to do something like this. I have an equivalent of fractions. They are equal. All right, I'm going to draw a couple of triangles and show you how to identify or show that they are similar. And we show that they are similar by showing that they are proportional. When I show that they are proportional, that just means that I do the corresponding sides and show that they are equal. I create this little skeleton. So if I had these two triangles, now they look like right triangles because it looks like a right angle in there, but the measurements that I'm choosing here probably doesn't prove that they're right triangles. So just keep that in mind, those of you that know the Pythagorean theorem.
Is it 20 or 2D?
20. All right, so these are two triangles, and they sure look similar, don't they? One just looks bigger than the other, but to show it, and you don't always have to show it, but sometimes it'll say show that these two triangles are similar. What I need to say, I need to check to make sure that their corresponding sides are proportional. So I would say, yep.
Does it have to be like a factor of the other one?
This one happens to be, just to make it easy, yeah. But you really, when you show proportional, you check cross product is what our main goal is.
But there is no cross
Okay,
product.
oh, there will be, because look at, when we say proportional, we always have that skeleton. So I would say 6, this side is to what side?
3.
3. 6 is to 3 as, and let me just go ahead and do the hypotenuse, as 20 is to what?
10.
10. Okay, now I want to see, are they proportional? That means are their cross products equal? Does 6 times 10, that's me multiplying the diagonal, equal the next one? 3 times 20.
Yes.
Yes. So they are proportional. And if they are proportional, then they are similar. Okay? So if they are proportional, they are similar. So, similar. Now that's the more advanced. I started you out hard right away. I'm going to get to the part where many 7th graders love this part. Because it's way easier. Okay? And it's solving for missing side lengths.
Wait, what do you do with the 8 and a 4? You just
Well, you can always create another proportion. What do you do? I could say, let's create another proportion. 8 is to what? 8 is to what?
8 is to 4.
4 as, and then I'm going to say 6 is to 3. You can pick any side lengths you want. And then I say, okay, are they proportional? Are they similar? Does 8 times 3 equal 4 times 6?
Yes.
24 does equal 24, so yes. So I just usually pick 2 of them. Yeah.
Like, on the bigger one,
Mm-hmm.
all the sides are just doubled. Could that be?
It won't always be that way. I
know, but like, if it was, could you just like automatically say?
Yeah.
or something?
If it was, if you can use your mental math and say, hey, I multiplied all of these by 2 to get to the other, then yeah, you know they're similar. But I'm just showing you the easy way.
Do you want us to show our work like that too?
Not if you can do it in your head. Ones like that. But there's ones that you can't. Solving with similar figures. What you need to do is create a proportion. Last heading of the day. I know we're crunched on time here, but I promise you that you only have 10 questions, and many students get them done very fast for their homework. So don't let yourself feel overwhelmed. You need to know this slide in order to be successful with your homework, though.
Do you write the pictures too?
All right, when I solve for similar triangles, my goal is to always create a proportion. So I always just write a skeleton proportion thing. So it says to find x. Well, let me just go ahead and start with side lengths I know. And I say 10 is to what?
X.
X, right? 10 is to this. As, the equals means as, this means as. As, then I go back to the original, 6
Is to 12.
is to what?
12.
6 is to 12. And then I solve, as we normally do.
So, what
So
do
you go, x would be equal to 10 times 12 and divided by 6. 120 divided by 6 looks like 20. X equals 20. Okay. Gonna do one more example, and I think that you will be doing well. Yes.
So it doesn't matter about the ABC.
No, right? I didn't care. I didn't care at all. Okay? So I want to do another one, but I want to make sure that I'm rotating it a little bit.
Didn't even get these up.
I know we didn't. Okay. Let's say that these are similar, and I have 5, 6, 7, 9, 10, 11. Oh, just kidding. I need to have an X in there. All right. Now, here's another one. I would specify these two triangles are similar. That means I can solve with a proportion. Okay? Now, I want to solve for x here. So I would say 5 is to what? What is 5 to?
X.
X, right? Now you need to be able to visually turn that around. 5 is to x as 6. What is 6 to?
9.
As 6 is to 9. And then solve with cross products.